Okay, so chemistry today. Woohoo! Okay, so today's task. We are going to start chapter 4. Is it sharing? Mm-hmm. Woohoo! Okay, so we are going to start chapter 4 today. It is about ideal gas. Everybody in Chem 1 or have completed Chem 1, what do we know about ideal gases? And other things. True. Okay, so now today my task is to develop stuff for the ideal gas and tell you what physics thinks ideal gases do. Okay, so here we go. So we will talk about gas laws, the ideal gas, microscopic model of the ideal gas, and the state properties of the ideal gas. So how many states can matter exist in? No. And how many of them are important to us? I'm going to ignore these two. Solid, liquids, and gases. And also plasma, but we don't care about that for now. So solids and liquids are called condensed phases. And gases, we can call them fluids, but fluids that can expand freely and fill any space available to them. In this chapter, we will be talking about the gas phase. So there were a lot of experiments done at the beginning, around the 17th and 18th century about gases. And this is a summary of everything we know. So experimental gas laws. Number 1. At constant temperature, volume inversely proportional. So at constant temperature, the volume is inversely proportional to the pressure of a gas. That is called Boyle's law. Number 2, at constant pressure, volume is proportional to the temperature of any gas. That's called the Charles law. Number 3, at constant volume, pressure is directly proportional to temperature. And that is called Gay-Lussac's law. Okay. Number 4, at constant pressure and temperature, volume is directly proportional to the number of molecules. And that is called the Avogadro law. So far, so good? Okay, Now, can I combine all of these laws together? The answer is yes, I can. P is proportional to T, proportional to N, inversely proportional to V. And how do I get rid of a proportionality in an equation? I put a constant there. That constant is called K. Or drum roll, PV equals nRT. And that's called the ideal gas law.
Why is it K? No.
Because we are talking about the number of molecules yet. Where this is the actual number of molecules. Now, we have a problem. How do you count the number of molecules in this room? One by one. Do you want to calculate the number of molecules in this room?
I'm okay.
So then what do we do?
Figure out the densities. You hope for the best.
PV equals nRT. You come up with a different constant, and instead of talking about every single molecule in this room, what do you instead want to talk about? The number of moles. And what is a mole? 6.022 times 10 to the 23. In this case, what will this be? Excellent. So that means K and R are somewhat related. So when you have the number of molecules, you use the value of K, which is 1.38 times 10 to the minus 23 joules per Kelvin. Whereas when you use R is, anyone remember? 8.31 joule mole per Kelvin. This is also known as the universal gas constant. And so most general chemistry textbooks use this form of the ideal gas law. So you've seen this a bunch of times.